Right now, you are sitting still. Your feet are flat on the floor. You are not floating away, and you are not being crushed flat. You never stop to ask why. You just assume the ground has you. That assumption is one of the biggest lies in physics. 400 years ago, Galileo was the first person to look closely at this and notice something strange. Drop a heavy object and a light one made of completely different materials, and they hit the ground at exactly the same moment. Legend says he proved it by dropping 2 iron balls off the Leaning Tower of Pisa. That story probably never happened the way you've heard it. It comes from Galileo's student, Vincenzo Viviani, who wrote it down in a biography years later. Galileo's own writings never mention it. Whether the tower story is true or not, the discovery underneath it is real. Weight, material, shape, none of it matters. A speck of dust, a feather, and a cannonball all fall at the same rate once you take air out of the equation. More than a century later, an apple supposedly fell on Isaac Newton's head. He realized the force pulling that apple down and the force keeping the moon in orbit around Earth were the same force. He called it universal gravitation, and he wrote an equation for it that predicted planetary orbits with stunning accuracy. Astronomers ran the numbers, and every object in the sky obeyed the formula. Newton looked like he had cracked open the universe's user manual. What could possibly be left for this equation not to explain? Mercury, as it turned out. Astronomers noticed that Mercury's orbit drifted by about 50 arc seconds every century, more than Newton's math predicted. The gap was tiny. It was also impossible to make disappear no matter how carefully anyone measured or recalculated. A theory that had ruled physics for 200 years had just developed a crack. Then a second problem showed up: light. Light has no mass, and Newton's formula was explicit that only mass gets pulled by gravity. Yet astronomers watched light bend as it passed near massive objects and near a black hole. It didn't just bend, it vanished completely, never to escape. How does something with zero mass get caught by a force that only works on mass? Universal gravitation was starting to fall apart. The person who actually fixed it was Albert Einstein, and he did it by throwing out your intuition about time and space. Newton treated time and space as a fixed, unchanging backdrop. Einstein said they were soft, stretchable, bendable. He also made a claim that sounds almost too strange to be useful. Acceleration and gravity are the same thing, indistinguishable from the inside. Put a person inside a spinning space station, and centrifugal force presses them against the wall exactly the way gravity would. That's not a coincidence. It's why, in Interstellar, the crew spins their ship on the long trip to Saturn. You can't survive 2 years with no gravity at all, so you fake it with spin. So why does more mass mean slower time? Because gravity itself drags time down. Move faster, and your effective gravity increases, so your time slows. Sit closer to a massive object, and the same thing happens. That's the real reason a black hole's neighborhood runs slow. You don't need to calculate some impossible orbital speed to explain it. You just need to know it has gravity, and that gravity gets stronger the closer you get. It's also the real explanation for Mercury. Mercury sits so close to the sun that it's under enormous gravitational pull, which means time runs measurably slower there. Once you factor that time distortion back into the math, Mercury's orbit lines up perfectly. So what actually is gravity? Einstein's answer turned out to be almost embarrassingly simple. There's no pulling force at all. Anything with mass just presses a dent into the space around it. Earth doesn't orbit the sun because the two objects attract each other. It orbits because the sun has bent the space nearby into a slope, and Earth is stuck sliding along that slope, unable to break free. Light bends for the same reason. It isn't being pulled, it's just following a curve that was already there. This single idea patched every hole Newton had left behind. Einstein made one more prediction. If massive objects can dent space, then moving massive objects should send ripples through it, the same way a stone thrown into a pond sends ripples across the surface. He called them gravitational waves, but according to his own math, those ripples would be almost impossibly faint. Even 2 colliding black holes would only produce a wave that, by the time it reached Earth, would be roughly the size of a single proton measured across the entire distance between Earth and the sun. for 99 years, nobody could detect it. Then in 2015, 2 observatories in the United States, each with arms 4 kilometers long, positioned thousands of kilometers apart, picked up an impossibly faint tremor at the exact same instant. It had traveled 3 billion light years from 2 black holes slamming into each other. Physicist Kip Thorne was one of the key figures behind that research, and he later became the science consultant for Interstellar. 3 years after the detection, the discovery won the Nobel Prize in Physics. What happens after 2 black holes collide? They merge into one larger black hole, which means the dark, empty-looking corners of the universe are probably far more crowded than anyone assumed. There's no way to know in advance whether the next thing that vanishes into the dark will be something close to home. That uncertainty is exactly what another physicist, Roger Penrose, spent much of his career trying to resolve. Einstein's equations hit a dead end at the center of a black hole, a singularity, a point of infinite mass and 0 size. The math simply breaks down there, and you can never actually see it because it's sealed inside the event horizon. Penrose proposed something bold, that the universe enforces a kind of built-in censorship. Anything that would violate physical law, anything that would break cause and effect, either gets hidden forever or simply cannot exist. If that's true, the future was determined the moment the past happened. Every choice you make today was already locked in by everything that came before it. It's also why the classic time travel paradox, going back and killing your own grandfather, is close to physically impossible. The universe has no room for a loophole that tears its own causal chain apart. In 2020, Penrose won the Nobel Prize in Physics for this work. So how strong is gravity really? Here's the part that might surprise you. Of the 4 fundamental forces in the universe, gravity is the weakest by far. The strong force locks protons together inside an atomic nucleus so tightly that prying one open takes a particle accelerator running on enough electricity to power an entire city. The weak force governs radioactive decay. The electromagnetic force is strong enough that a piece of plastic rubbed against your hair can lift a scrap of paper off a table, instantly beating out the gravitational pull of the entire planet. And gravity, it holds the moon, the earth, the whole solar system together, and yet it's too weak to pull a speck of dust toward your outstretched hand. Physicists believe all 4 forces were a single force at the very beginning of the universe before it expanded and cooled into the 4 we see today. The weak force and the electromagnetic force were successfully unified decades ago. Physicists are still working to fold the strong force in, and gravity remains the hardest piece of all, mostly because it's the one scientists understand the least. The leading theory right now is that gravity is the only force capable of leaking across dimensions. If the universe has more than the 3 spatial dimensions you can perceive, gravity's strength may be getting diluted, spread thin across dimensions you'll never see, leaving only a faint trace behind in your own. That's the same idea Interstellar leans on. A father stranded in a 5-dimensional space with no way to reach his 4-dimensional daughter through light or radio, reaching her instead through gravity because gravity is the one force that can cross from one dimension into another. So the next time you're sitting still, feet flat on the floor, it might be worth reconsidering what's actually holding you there. It was never a rope, and it was never a frame. It's the space beneath you, quietly curved, and that curve may already be reaching into a dimension you will never be able to see.